Michelle Crummell, and today we're going to look at some of the algebra and trigonometry skills you'll need to be successful in calculus. Let's start by talking about notation. Now in algebra, you're used to using letters from the English alphabet like X, Y, W, Z, S, T, A, B, C, etc. to stand in place of variables. In calculus, we often use Greek letters instead of letters from our English alphabet, so we want to be able to recognize those and call them by their proper names. We'll start with alpha. Alpha is a lowercase letter in the Greek alphabet. And then we have beta, also a lowercase letter. Now we're going to be using delta as an uppercase letter and a lowercase letter. So two different symbols for delta. Uppercase delta looks like a triangle, and this is the lowercase delta. And we have epsilon, which looks like this, and depending on your font, it might also look like this. Pi, we've used in geometry. Theta, you've probably used in trigonometry. And we'll also be using the uppercase sigma as our summation symbol. The next thing we're going to look at is factoring. And before we get started with our exercises, let's just review some of our factoring formulas. If we have the quantity a squared minus b squared, we call that the difference of two squares, and that factors as a plus b times a minus b. We also have a formula for factoring the difference of cubes. A minus b times a squared plus ab plus b squared. And we have an acronym to help you remember the signs there. Same sign, opposite sign, and then the last sign is always positive. So SOAP. There's a similar formula for factoring the sum of cubes. And again, we can use the SOAP acronym. It's a plus b, we use the same sign, and then a squared minus the opposite sign, a times b, plus, this last one is always positive, b squared. Now we have some more advanced versions of our difference of squares formula. For example, we might see a to the fourth minus b to the fourth. That is still the difference of two perfect squares, which would factor as a squared plus b squared times a squared minus b squared. But a squared minus b squared is also the difference of squares, so we would factor that further. The a squared minus b squared becomes a plus b times a minus b. And we say that's factored completely. You could also apply the difference of squares formula to something like a minus b. Now that doesn't look like perfect squares, but we can still use the square root of a and factor it like root a plus root b times root a minus root b. So those are just some formulas to keep in mind as we work through the following exercises. Number 2, we want to factor 9x squared minus 16y squared. This is the difference of two squares. So it factors as, we take the square root of 9x squared, plus, then we take the square root of 16y squared, so 3x plus 4y times 3x minus 4y. Number 3, we want to factor x squared minus x plus h squared. This is also the difference of two squares. So it's x plus, then the square root of x plus h squared is x plus h, and x minus the quantity x plus h. That simplifies. Here we're going to combine like terms, so we have 2x plus h times, and here when we distribute our negative, we're just left with negative h. 4. X squared minus 12xy plus 36y squared. This one is a perfect binomial square. So it's x minus 6y squared. If you were to multiply that back out, remember for a problem like this, you have to FOIL it out. So first times first gives you x squared, and then the outer product will be negative 6xy. The inner product is also negative 6xy, combine like terms to negative 12xy, and then last times last is 36y squared. Number 5, 20 minus x squared. I usually prefer to factor when the leading coefficient is positive. So my first step here is to factor out a negative 1, and then I will rearrange the terms so the exponents appear in descending order. And then factor x squared plus x minus 20. Since the leading coefficient here is a 1, the only way to get x squared is x times x. I just have to figure out what these last two coefficients are. So 20, it could be 1 and 20, 2 and 10, 4 and 5. I'm looking for a pair that multiplies to 20 and whose sum or difference is positive 1. So it looks like 4 and 5. Since I want a positive 1, I want positive 5 and negative 4. Number 6, x to the power 4 minus 10x squared plus 9. Now to get x to the 4th, since the leading coefficient is 1, I'm guessing it's going to be x squared times x squared. And then 9, it could be 1 and 9 or 3 and 3, but I want to get a 10 in the middle. So 3 and 3 is not going to give me a sum or difference of 10. It'll be 1 and 9. Since I want negative 10 in the middle, these are both negative. Now x squared minus 1 is the difference of two squares. It can be factored further. So is x squared minus 9. So we'll keep going with this one. We have x plus 1 times x minus 1 times x plus 3 times x minus 3. Number 7, 2x squared minus x minus 6. So this time my leading term is 2x squared. I'm going to have 1 times 2, so an x and a 2x. And then 6, it could be 1 and 6, it could be 2 and 3. I'm trying to get a negative 1 in the middle. So this is the 1 times 2. This could be 1 times 6 or 2 times 3. Well, if I do 2 times 2 and then 1 times 3, that would be a 4 and a 3, and the difference is 1. So I believe that's the one that's going to work. So 1 has to get multiplied by 3. That puts the 3 as part of the outer product. And this 2 has to get multiplied by this 2. So that puts that for my inner product. I want a negative 1 in the middle. So I want negative 4x and positive 3x. Number 8, we want to factor 8x cubed minus 27y cubed. This is the difference of cubes. We're going to use our difference of cubes formula. The cube root here is 2x, and the cube root of 27y cubed is 3y. So this factors as 2x minus 3y times the quantity 2x squared is 4x squared. And then I multiply these two together, so I get negative 6xy. But remember, we want to use the opposite sign here. So 6xy. And then the last one is always positive. And for that, I'm going to square this. So plus 9y squared. Number 9. We're going to factor the quantity x plus h cubed minus x cubed. This is the difference of cubes. So I have x plus h minus x using the same sign. And then I square this quantity. So x plus h squared. I use the opposite sign. and then the product of these two, x times x plus h, plus, the last is always positive, I square this root. And now we'll simplify. So x plus h minus x is just h. X plus h squared, the quantity x plus h squared. So I'm going to FOIL that out. It's x squared plus 2xh plus h squared. Plus, now I'm going to distribute this x. So x squared plus xh plus x squared. And we'll combine like terms. So I have this x squared and this x squared and this x squared combined to give me 3x squared. I have a 2xh and an xh combined to give me 3xh. And then plus h squared. Number 10, we want to factor x plus ay plus x squared minus a squared y squared. Notice that these two terms are the difference of two squares. So let's factor that part of it. X plus ay plus, then we have x plus ay times x minus ay. Now I can factor by grouping. I've got an x plus ay here and an x plus ay here. So I'm going to factor the x plus ay out. And see what we have left. So when I factor out, really I'm dividing by. So x plus ay divided by x plus ay is just 1. Plus, and then from this second term right here, when I factor out an x plus ay, remember that just means dividing by x plus ay, I'm left with x minus ay. And now this is factored. It's one term multiplied by another term. It's the product of two factors. 11. 3x cubed times x minus 7 cubed plus 4x squared times the quantity x minus 7 to the fourth. Now here we have some common factors in each one of these terms. So I'm going to factor out the greatest common factor, which is x squared times x minus 7 cubed. That's what I'm factoring out of each of these terms. When I factor it out of this term, remember factoring out means dividing by. So when I divide this by x squared, I'm left with a 3x. And I'm also dividing it by x minus 7 cubed, and that's going to cancel out this x minus 7 cubed here. So plus, and then I move on to my next term. I'm factoring out x squared times the quantity x minus 7 cubed. So dividing by the x squared gets rid of this x squared entirely, leaves me with 4. And then when I'm dividing by the x minus 7 cubed, I'm left with a single quantity x minus 7. And we have some like terms that can be combined there. So x squared, the quantity x minus 7 cubed, times, and then when I distribute the 4 here, I have a 3x plus 4x, that gives me 7x, and minus 28. We can also factor a 7 out of this factor, 7x minus 28. So our final answer in completely factored form would look like 7x squared times x minus 7, that quantity cubed, times x minus 4. Number 12, 5x to the power 2/3 minus 4x to the power 1/3. I'm going to factor out the greatest common factor, which is x to the power 1/3. And remember, factoring out an x to the 1/3 means I'm dividing each term by x to the 1/3. So I have 5x to the 2/3 divided by x to the 1/3. We can use our rule for dividing numbers with the same base. We subtract the exponent, so 2/3 minus 1/3 leaves me with 1/3. Minus, and then it's 4x to the 1/3. I'm dividing that by x to the 1/3. It's just going to leave me with the 4. Number 13, x times the quantity x plus 3 to the power -1/2 plus 2 times x plus 3 to the power 1/2. So here my greatest common factor is the quantity x plus 3 to the power -1/2. So I'm dividing each term by that. The first term here, when I divide by x plus 3 to the -1/2, I'm left with just x. And the second term, when I divide by x plus 3 to the -1/2, I'm going to subtract my exponents. So 1/2 minus -1/2, that double negative makes it 1/2 plus 1/2, which is 1. And then we have like terms that can be combined. So when I distribute the 2 here, leaves me with 3x plus 6. Now I can factor out a 3 from there, leaving me with the quantity x plus 2. In this next set of exercises, we're going to look at simplifying fractions. And oftentimes in calculus, you're going to have to simplify complex fractions. So we'll see those in a moment. But first of all, let's just remember, if you have a plus b over c, that fraction can be separated. It can be split into two separate fractions, a over c plus b over c. However, if you have one term in your numerator and two terms in your denominator, you cannot separate that. Okay, so let's get started with number 14. X squared plus 3x over x squared. We want to simplify this fraction. So we are going to split it up. X squared over x squared is 1 plus, and then we have 3x over x squared, which can be further simplified. So 1 plus 3 over x. Number 15, simplify ab squared minus ba squared over a minus b. In the numerator, we can factor out the common factor ab, leaving us with b minus a. Now we have a factor of b minus a in the numerator and a minus b in the denominator. These are opposites. So I can factor a -1 out of the top, and that b minus a becomes a minus b. Now I have a common factor in the numerator and denominator that we can cancel out, leaving us with just -ab. Number 16, x squared plus x minus 6 over x plus 3. I'm going to factor the numerator, and that will factor as x plus 3 times x minus 2 over x plus 3, and that common factor x plus 3 we can remove, leaving us with just x minus 2. X squared plus 2x minus 4 over square root of x. When you have more than one term in the numerator and one term in the denominator, you can separate this into multiple fractions. So it becomes x squared over square root of x plus 2x over square root of x minus 4 over square root of x. Now we want to simplify this, and there's a few ways that we can do this. I can convert from radical notation into fractional exponent notation. So then it would look like x squared over x to the power 1/2 plus 2x over x to the power 1/2 minus 4 over x to the power 1/2. And then we can subtract our exponents since we have like bases in our first term. So 2 minus 1/2 leaves me with 3/2, so x to the 3/2 plus, and then here in the second term, it's x to the power 1 divided by x to the power 1/2, subtracting our exponents there, leaves us with x to the power 1/2. And then for this last term, now in algebra, when you're simplifying, you're normally taught not to keep negative exponents in your answer. But in calculus, oftentimes we're going to want to bring that term up to the numerator. So for now, I'm going to write it as 4x to the power negative 1/2. Now I didn't have to convert to fractional exponents. I could also have just simplified this in this middle term, for example. When I see x divided by root x, I'm thinking of x as the square root of x times the square root of x, and I'm dividing that by the square root of x. So one of those roots just cancels out, leaving me with 2 root x. So I could have written that in radical form as 2 root x. In radical form, x to the power 3/2 is the square root of x cubed. And then x to the power negative 1/2. So if I were going to write in radical form, I would probably move that down to the denominator and write it as 4 over the square root of x. Number 18, 2x minus square root of x plus 3 all over x. So here we're going to separate this into 3 fractions. 2x divided by x is 2, minus square root of x divided by x is 1 over root x, plus 3 over x. And it's fine to leave your answer like that. Again, in calculus, sometimes we have a reason to bring those terms up into the numerator. And we also sometimes prefer to work with fractional exponents. So we could also write this as 2 minus x to the power negative 1/2 plus 3x to the power negative 1. Number 19, and here we see our first complex fraction. A complex fraction is when you have a fraction inside of a fraction. And there are a couple of ways that you can simplify complex fractions. I like to use the least common denominator method, where I'm going to look at the inner fraction, or sometimes there's multiple inner fractions, and find the least common denominator, which in this case is x minus 1. So I'm going to multiply the entire outer fraction by x minus 1 over x minus 1, which is just a fancy form of the number 1. When we multiply fractions, we multiply the numerators, and then we multiply the denominators. So when I multiply the numerators here, I'm going to distribute the x minus 1 to the 1, which will give me x minus 1, plus, and then I'm going to distribute the x minus 1 to this 1 over x minus 1. The denominator will cancel out, and that leaves me with just plus 1. In the denominator, when I multiply, I have x times x minus 1. So combining like terms in the numerator, now I have x over x times x minus 1. The x's cancel out, that's a common factor. And my final answer will be 1 over x minus 1. Number 20, a minus b over square root of c all over c. So again, I'm looking to see what is that least common denominator. In this case, it's square root of c. So I'm going to multiply the outer function, or the outer fraction, by root c over root c. Okay, I'm going to distribute square root of c to the a, so get a root c. Then I distribute that to the minus b over root c, which leaves me with just minus b. Over, and on the bottom, I have c root c. Okay, we can separate this into a root c over c root c minus b over c root c, which simplifies to a over c minus b over c root c. Square root of c minus b over 2 root c all over square root of c squared. Okay, so again, I'm looking for that LCD, my least common denominator, which is 2 root c. So I'm going to multiply the outside fraction by 2 root c over 2 root c. Okay, so I'm going to distribute the 2 root c to this first term, and that'll give me 2c minus, and then I'm distributing it to this second term, which will just give me b, over. Now on the bottom, root c squared is just c, so I have 2c root c. We could leave it like that, or we could separate it into two fractions, 2c over 2c root c minus b over 2c root c equals, so here my 2's cancel out, the c's cancel out, so I have 1 over square root of c minus b over 2c square root c. 22, x plus y over 1 over x plus 1 over y. So here my least common denominator for those inside fractions is xy. So I'm going to multiply the outer fraction by xy over xy. Okay, so on the top, I distribute xy to the x, I get x squared y, plus, then I distribute xy to the y, I get xy squared, over, on the bottom I'm also going to distribute xy times 1 over x is just y, plus, and then xy times 1 over y is just x. And number 23, if x over 1 minus 1 over 1 plus x over y. So we have a fraction inside of a fraction inside of a fraction. I'm going to start by multiplying by this denominator here, the whole outer fraction, by 1 plus x over y over 1 plus x over y. So in my numerator, I'm distributing, I get x plus x squared over y over, now in the denominator, okay, I'm distributing this to the 1 first, so I have 1 plus x over y minus, and now I distribute that to this term, the denominator cancels out, so I just have a 1. So it's x plus x squared over y over the 1 minus 1 in the denominator cancels out, so I have x over y. Now I'm going to continue to simplify. The least common denominator now is just y, so I'm going to multiply the outside fraction by y over y. So I distribute the y to each of those terms. I get xy plus x squared over, and then on the bottom, x over y times y is just x. I can factor out an x in the numerator, so x times y plus x, and then one of the x's cancels out, and my final answer here is just x plus y. Next, we're reviewing problems that involve functions and equations. Number 24. If f of x equals x cubed plus 5x minus 1, then find f of 1 minus f of 0. F of 1 means we substitute 1 in for x, so we have 1 cubed plus 5 times 1 minus 1. That quantity minus, and f of 0 means we're going to substitute 0 in for the x. So 0 cubed plus 5 times 0 minus 1. You can probably do this type of problem in your head, so you really don't need to write out all of these steps, but just to be clear, I'm going to go ahead and do that. Minus, and I'm distributing the negative sign. So we have 1 plus 5 minus 1 plus 1, which is 6. Number 25, if f of x equals x squared minus 3x plus 1, then f of x plus h minus f of x equals. So first let's find f of x plus h. F of x plus h means we substitute x plus h in for the x. This is our new input. The rule for f is input squared minus 3 times input plus 1. So my input is x plus h. That means f of x plus h is the quantity x plus h squared minus 3 times the quantity x plus h plus 1. And then I can expand that. I get x squared plus 2xh plus h squared. I distribute the negative 3. So minus 3x minus 3h plus 1. And I combine any like terms. I don't see any like terms. So that's my f of x plus h. The f of x plus h minus f of x, it means I have x squared plus 2xh plus h squared minus 3x minus 3h plus 1, all of that minus my f of x, which is x squared minus 3x plus 1. So here I am going to distribute now this negative 1 and combine like terms. So minus x squared, tell you what, I'm going to write it underneath the like terms. So minus x squared is here. Then I have a plus 3x here, and I have a minus 1 here. So conveniently, those things cancel out, leaving me with 2xh plus h squared minus 3h. Number 26. If f of x equals 1 over 2x, then find f of x plus a minus f of x over a. Well, f of x plus a just means the input for function f is x plus a, and the rule for function f is 1 over 2 times input. So f of x plus a is 1 over 2 times the quantity x plus a. And then f of x plus a minus f of x all over a would be 1 over 2 times x plus a minus 1 over 2x all over a. This is a complex fraction, so we saw earlier to simplify a complex fraction, we identify the least common denominator, which in this case is 2x times x plus a, and we're going to multiply the numerator and denominator of the outside fraction by the LCD. So we're going to distribute this on the top, and then we also have to multiply it on the bottom. On the top, when I multiply 1 over 2 times the quantity x plus a times my LCD, the 2's cancel, the x plus a's cancel, and I'm just left with an x. Minus, when I distribute it to the negative 1 over 2x, the 2's cancel, the x's cancel, and so I'm left with an x plus a. In the denominator, I have 2 times a times x times the quantity x plus a. Now I'm not going to distribute any further in the denominator because I'm hoping something's going to cancel out. In the numerator, I will distribute this negative 1. X minus x is 0 minus a. So I have minus a over 2ax times x plus a. And sure enough, the a's cancel here, leaving me with a final answer of negative 1 over 2x times x plus a. Number 27, f of x equals the square root of x plus 5. And we want to find f of x plus h minus f of x all over h. So let's first find f of x plus h. The rule for f is square root of input plus 5. And our input is x plus h. Okay, so now we can build f of x plus h minus f of x over h. That's going to be the square root of x plus h plus 5. I can drop the parentheses since I'm not distributing anything. Minus f of x, so square root of x plus 5 over h. Now to simplify this, we're going to multiply top and bottom by the conjugate of the numerator. So the conjugate will be square root of x plus h plus 5 plus the square root of x plus 5. I'm just using the opposite sign in between those two terms. We're multiplying top and bottom because this is really just a fancy form of the number 1. And multiplying by 1 doesn't change the value of the fraction. Okay, so here I am going to have to distribute, and we can kind of organize our work doing FOILs. So first times first, then the outside product, the inside product, and then the last times last. Square root of x plus h plus 5 times itself is just x plus h plus 5. The outside product and the inside product match, except one is positive and one is negative, so they cancel out. Minus, and then last times last, we're multiplying square root of x plus 5 times square root of x plus 5, so we just get x plus 5 over h times the quantity, square root x plus h plus 5 plus square root x plus 5. I'm not going to distribute that h because I'm hoping the h will cancel out once I simplify in my numerator. And in the numerator, we can distribute this negative 1. So we have a positive x minus x, that's 0. We have h, and then we have positive 5 minus 5, which is 0. So just an h left in the numerator. And h times square root x plus h plus 5 plus square root x plus 5. In the denominator, the h's cancel. And I have 1 over square root x plus h plus 5 plus square root x plus 5 as my final answer. 28. 3x cubed a plus 9x squared y minus 4a minus 2 equals 0. We want to solve for a. So we're going to group the two terms that have an a together, 3x cubed a minus 4a, and we're going to move the remaining terms to the other side of the equation, equals. So I'm going to add 2 to both sides, then I'm going to subtract 9x squared y from both sides. Now I factor out the a on the left, leaving me with 3x cubed minus 4. And finally, to isolate the a, I'm going to divide both sides by 3x cubed minus 4. So I have a equals 2 minus 9x squared y over 3x cubed minus 4. 29. Solve 4x times 10 minus 2x plus 10 minus 2x quantity squared equals 0. First thing we'll do is factor out what they both have in common. So 10 minus 2x. From the first term, that leaves me with 4x. When I factor it from the second term, that leaves 10 minus 2x. 0, we can combine like terms. So I have 10 minus 2x times 2x plus 10 equals 0. And now that this is completely factored, well, it's not completely factored, I could still factor a 2 from each one of these factors. But now that it's in factored form and it's equal to 0, I solve by setting each factor equal to 0. So 10 minus 2x equals 0 when x equals 5, and 2x plus 10 equals 0 when x equals negative 5. Those are my two solutions. Number 30. Solve 12x equals x squared. Now it might be tempting to start this problem by dividing both sides by x, but algebraically that's not a smart move, because what if x is equal to 0? If x is equal to 0 and you divide both sides by x, then you've just divided by 0, which is not allowed. So the correct way to solve this equation would be to rearrange your terms so that one side of the equation is equal to 0. So what we're going to do is subtract 12x on both sides, and that will give us x squared minus 12x equals 0. Now we can factor out an x. X times x minus 12 equals 0. And then we set each factor equal to 0. So we have x equals 0 or x minus 12 equals 0. In other words, x equals 12. Number 31. Use long division to rewrite 2x to the power 4 plus 3x cubed minus x squared minus 1 over x minus 2. So this is polynomial long division, but the algorithm is very similar to the algorithm you use when you're doing long division of numbers. So we set it up as 2x to the 4th plus 3x cubed minus x squared. You might want to put a placeholder term for the linear term. It's not absolutely necessary, but it'll help you keep your work organized. We are dividing that by x minus 2. So to start, we want to know what would we multiply x by to get a perfect match here with 2x to the power 4. Well, I would have to multiply x by 2x cubed. And the place value for x cubed is here. So I'm going to write my 2x cubed in the proper place value area. Now, the algorithm is we take this 2x cubed and we multiply it by our divisor, the x minus 2. So I have to distribute the 2x cubed to the x minus 2. And I'm going to write that down here. So 2x cubed times x is 2x to the power 4. 2x cubed times negative 2 is negative 4x cubed. Now we're going to subtract. I prefer to add the opposite instead of subtracting. So I'm going to use the opposite signs here and add the terms instead. So I have 2x to the 4th minus 2x to the 4th. That cancels out and gives me 0. Then I have 3x cubed plus 4x cubed. That gives me 7x cubed. 7x cubed is not my remainder because it's degree 3 and my divisor is degree 1. I haven't reached my remainder until this quantity has a smaller degree than what I'm dividing by. So I'm going to go again. I just repeat the process again. So I ask myself, what do I multiply x by to get 7x cubed? And the answer is 7x squared. So I write the 7x squared here over the x squared place value spot. And I multiply my 7x squared by my divisor, x minus 2. And when I do that, I get 7x cubed minus 14x squared. And I should have said that we bring down this next value here. Okay. Now I need to subtract. So instead of subtracting, I'm going to add the opposite. So I use the opposite signs and then I add. 7x cubed minus 7x cubed is 0. Negative x squared plus 14x squared is 13x squared. Then I bring down the next term, which is a 0x. And I go again. This is not yet my remainder because x squared is a higher degree than x. So what do I multiply x by to get 13x squared? Well, I would multiply it by 13x. It's 13x. Now I take my 13x and I multiply it by my divisor x minus 2. And I get 13x squared minus 26x. Now I need to subtract, but I'm going to add the opposite instead. So 13x squared plus negative 13x squared is 0. 0x plus 26x is 26x. I'm going to bring down my last term and go again. This is not yet my remainder because this is degree 1 and my divisor is also degree 1. So I go again. What do I multiply x by to get 26x? I multiply it by 26. Now I'm going to take the 26, multiply it by the divisor. I get 26x minus 26 times 2 is 52. And I need to subtract there. I'm going to add the opposite. So 26x minus 26x is 0. Negative 1 and 52 is a positive 51. Now this constant term has degree 0, and my divisor has degree 1. So at this point, this is not my remainder. My remainder term is going to look like 51 over the divisor, x minus 2. So the question asked us to use long division to rewrite 2x to the fourth plus 3x cubed minus x squared minus 1 all over x minus 2. And this would be our final answer here. Maybe I'll write it again at the bottom. 2x cubed plus 7x squared plus 13x plus 26 plus 51 over x minus 2. Number 32. We want to find the exact solutions of x cubed plus x squared minus 4x plus 2 equals 0. Now, if we had the use of a graphing calculator, we could graph this function and see where it was equal to 0. But without a calculator, we could rely on the rational roots theorem, knowing that if there are any rational roots, they're going to be plus or minus 1 or plus or minus 2. So just using substitution, if I put in a positive 1, I would have 1 plus 1 is 2, minus 4 is negative 2, plus 2 is 0. So x equals 1 is definitely a solution. Knowing that x equals 1 is a solution, I could now use polynomial long division to factor out the x minus 1 and try and solve the remaining quadratic. Or I could use synthetic division. Let's use synthetic division. To use synthetic division, I'm going to copy down the coefficients of my terms in descending order. 1, 1, negative 4, and 2. I'm going to divide by the root that I know, which is 1. I start by bringing down this first coefficient, 1, and then I multiply by the root, 1, and that gives me 1. Then I add the numbers in this column, I get 2. Then I repeat the process. 2 times 1 is 2, and I add the numbers in the column, negative 2. Negative 2 times 1 is negative 2, and I add and I get a remainder of 0, which is what I expected since 1 is a real root. So this tells me that my original equation factors into x minus 1 times, and now I use these new coefficients, x squared plus 2x minus 2. And to solve, remember, we set each factor equal to 0. So now I can use the quadratic formula to finish solving this. Or, without writing this out, I know that these coefficients represent the a, the b, and the c in my quadratic equation. So quadratic formula tells us that x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c over 2 times a. We can simplify this. Negative 2 plus or minus the square root. 4 plus 8 is 12 over 2, and that simplifies. Negative 2 plus or minus 2 root 3 over 2, or negative 1 plus or minus square root of 3. So my solutions are x equals 1 or negative 1 plus or minus square root of 3. Number 33, solve 1 over x minus 1 plus 1 over x plus 1 plus 2 over x squared minus 1 equals 0. I'm going to start by combining these three fractions into a single fraction. So the least common denominator is x squared minus 1. That makes this x plus 1 over x squared minus 1 plus x minus 1 over x squared minus 1 plus 2 over x squared minus 1 equals 0. Or x plus 1 plus x minus 1 plus 2 over x squared minus 1, which simplifies to 2x plus 2 over x squared minus 1. And I want to know, when does this equal 0? Well, a fraction can only equal 0 when its numerator is 0 and denominator not 0. So we want to know, when is 2x plus 2 equal to 0? And that is when x equals negative 1. However, if we let x equal negative 1, we run into a problem, because that would make the denominator equal to 0, which is not allowed. So let's use some algebra to keep working on this problem. If we completely factor our numerator and denominator, we get 2 times the quantity x plus 1 over x plus 1 times x minus 1. Now we have a common factor, this removable discontinuity, that we can eliminate. So we get 2 over x minus 1 equals 0. But again, a fraction can only equal 0 when its numerator is 0. And 2 will never equal 0. So this gives no solution. Number 34, we're asked to rationalize the denominator of the expression 1 plus square root of 2 over 1 minus square root of 2. To rationalize the denominator, we're going to multiply by the conjugate of the denominator. So the conjugate would be 1 plus square root of 2. Same terms, but opposite sign in the middle. We want to multiply top and bottom by that quantity so that we're not changing the value of the fraction. On the top, we need to FOIL that out. First times first is 1. The outside product is square root of 2. The inside product is also square root of 2. So 2 root 2 plus, and then the last times last is 2. In the denominator, we're going to create the difference of squares here. So first times first is 1. The outside and inside products cancel out. And the last times last is going to give us minus 2. So in the numerator, we have 3 plus 2 square root of 2. And in the denominator, we have negative 1. So negative 3 minus 2 times the square root of 2. Number 35, write the equation of the line passing through the points 1, 5 and 7, 12. Now there are multiple ways to represent the equation of a line. What we're going to need to know, if we want to use slope-intercept form or point-slope form, is the slope of the line. So let's find that first. The slope would be the change in y, so the change in y over the change in x. To find the change in y, I subtract the second y coordinate minus the first y coordinate. So 12 minus 5 over, and then 7 minus 1. The change in x, I take the second x coordinate minus the first x coordinate. 12 minus 5 is 7. 7 minus 1 is 6. So the slope of this line is 7 over 6. Now the easiest way to write the equation of the line would be point-slope formula, since I now know the slope and I have a point on the line. So I could use my first point 1, 5 and write the equation as y minus 5 equals my slope, 7 over 6, times the quantity x minus 1. Or if I were using the other point, the 7, 12, I could say y minus 12 equals 7 over 6 times x minus 7. And in calculus, we usually just use the point-slope formula. Number 36, write the equation of the line passing through the point 2, negative 4, and parallel to the line 6x plus 2y equals 11. We have a point on the line. We need to know the slope of the line. Well, if it's parallel to 6x plus 2y equals 11, then it has the same slope as 6x plus 2y equals 11. So I'm going to solve this equation for y. Y equals 11 minus 6x over 2. And now I can see from here that the slope of this line is negative 6 over 2, or negative 3. So the line I'm trying to write an equation for passes through 2, negative 4, and has a slope of negative 3. I'm going to use the point-slope formula. Y minus negative 4 equals the slope times x minus 2. 37. Write the equation of the line passing through the point 2, negative 4 and perpendicular to the line 6x plus 2y equals 11. Well, a perpendicular line has the opposite reciprocal slope. So if 6x plus 2y equals 11 has a slope of negative 3, then the slope of my perpendicular line is going to have the opposite slope, so positive and reciprocal, 1/3. And it passes through this point 2, negative 4. So again, I can use the point-slope formula. Y minus negative 4 equals 1/3 times x minus 2. Number 38, explain the difference between the reciprocal of x squared and the inverse of x squared. Let's look at the reciprocal of x squared. The reciprocal of x squared is 1 over x squared. If we do a rough sketch of x squared, y equals x squared, look like this, and the graph of the reciprocal looks quite different. The reciprocal has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And it looks something like this. So as x squared approaches 0, its reciprocal approaches infinity, and vice versa. Now the inverse of x squared, the inverse operation is going to undo what x squared does. So x squared takes an input value and squares it. The inverse of that, if we want to undo that, we're going to take the square root of our input value. So the inverse of x squared is square root of x, with the restriction that x must be greater than or equal to 0. So again, if we compare the graphs, we've got y equals x squared, and the graph of square root of x looks like this. So we can see that the reciprocal and the inverse really don't look anything like one another. They're two very different concepts. Number 39. Find f of g of x. F of g of x. If f of x equals x squared plus 3x, and g of x equals 2x minus 3. For f of g of x, our inside function is the g of x. So we're going to use g of x as our input. And now the rule for f of x is input squared plus 3 times input. And our input is g of x. So we need g of x squared plus 3 times g of x. g of x equals 2x minus 3. So it'll be 2x minus 3 squared plus 3 times 2x minus 3. Now we'll expand. Here we get 4x squared minus 12x plus 9, and we'll distribute the 3. So plus 6x minus 9. We can combine some like terms here. 4x squared minus 6x. And number 40, solve 3x squared plus 24x minus 12 equals 0 by completing the square. Well, I notice that all of these terms are divisible by 3, so I'm going to begin by factoring out a 3. And actually, I'm not going to bother factoring it out of the constant term. I'm trying to create a perfect square out of x squared plus 8x. So there is some constant that I need to add here to make this a perfect square. And that is going to be half of the middle coefficient, which is 4, squared. So 16. 16 is that magic number that I have to add in here to make this a perfect square. But by adding a 16 inside of the parentheses, I've really added 3 times 16 because that 3 gets distributed to that 16. So I have introduced an extra 48 into the left-hand side of this equation. And I have to balance that by adding a 48 to the other side of the equation. And now I'm ready to write this as a perfect square. So it's x plus 4, half of that middle term, squared, times the 3 in front, minus 12. I'm going to add 12 to both sides. So now it's 48 plus 12, which is 60. And I'm going to continue to solve from here. So I divide both sides by 3. I get x plus 4 squared equals 20. Now I can take the square root on both sides. I get x plus 4 equals the square root of 20. But when I take the square root of x plus 4 squared, I need to use a plus or minus. Rather than writing the plus or minus on the left-hand side of the equation, I'm going to write the plus or minus on the right-hand side of the equation. And so I have x equals negative 4 plus or minus the square root of 20. 20 is 4 times 5, which is 2 times the square root of 5. So my solutions, negative 4 plus 2 root 5 and negative 4 minus 2 root 5. So that concludes our review on factoring, simplifying fractions, and working with functions and equations. In the next installment, we'll look at writing formulas, working with inequalities and piecewise functions, graphing functions, exponents, exponential, and logarithmic functions, and then a review of trigonometry.